Short video on graphs of log functions with a focus on transformations of functions. For the purposes of this video, I'm going to use f of x equals log to the base 2x as the parent function. This just means that it's the position that we're starting with, the function that we're starting with, and then any transformations or changes that we make are being made to this original function. So let's just start off by reminding ourselves how this looks in graph form. So here's my starting point, my parent function, f of x equals log to the base 2x graphed. I've given myself a little bit of room above and below this function just to be able to show you the transformations clearly. And now I'm going to have a look at what happens when I change the function here slightly and what effect that'll have then in terms of the graph. So the first transformation that I'm going to have a look at is g of x equals log to the base 2x plus 1. Notice there's no bracket around the x plus 1, so it's log to the base 2x and then separately plus 1. You might also see this written as g of x equals f of x plus 1. If I add a constant to the end of any function, the effect that it has is it will move it vertically by that amount. So in this particular instance, I'm adding 1. So what that does is it moves every point up 1, plus 1. So here I've marked in my g of x points. And when I join them together, you can see that it looks pretty much exactly like the f of x function, just that it's been moved up a little bit. So here's my second example then. H of x is a function, which is our parent function log to the base 2x minus 1. Again, notice there is no bracket around the x minus 1, so it's the log minus 1. This can also be written as f of x minus 1. Again, in this case, when I'm amending the original parent function by putting a constant at the end, I'll move the function vertically by that amount. In this case, it's minus 1, so I'm going to move everything down one space. So I've marked my new points in for my function. And again, I join the points up and you can see again, this looks really like my original function. It's just that it's moved slightly downwards. Notice that in all of these cases, the y-axis is still being preserved as an asymptote. I'm still not crossing it. I'm approaching it. I'm getting very close, but I'm never touching it or crossing it. Lastly, let's look at the example of j of x, which is minus log to the base 2x. I could also write this as minus f of x. So in this case, what I'm going to do is I'm going to take every y point or every y value and multiply it by a minus. So let's see where they end up. Now I'm going back to my original parent function initially, which is my pink function here. And then I'm going to multiply the y values by minus 1. So the point here on the x-axis can stay put. This was 2, 1. So now I'm going to 2 minus 1. This was 4, 2. So now I'll go to 4 minus 2. This was 8, 3, so now I go down to 8 minus 3. And this was 16, 4, so then I go down to 16 minus 4, which is just there. And then I'll join these points together to create the function. So you can see that all that's happened really is that I've flipped my function over, and when it's something as simple as minus fx, what I'm effectively doing is that I'm using the x-axis as a line of symmetry through which to reflect my original function. Note that I'm still approaching the y-axis but not meeting it or crossing it. So in summary, multiplying a function by a minus, or minus 1 if you like, reflects it in the x-axis, and adding or subtracting a constant moves it vertically by that amount. If it's a plus, up, and if it's a minus, down. These are not the only types of transformations that can occur. You can multiply a function by a constant. For example, you might multiply f of x by 2, in which case you double all your y values and then replot.